Okay. Hello, everybody. This is lecture number 16. It is a continuation to the previous lecture, which was numbered 15. Reminding you with the last lecture, I have introduced you to the Rosenbrock function. We have plotted the function in a three-dimensional space in Python by using matplotlib. We have plotted the cost function as a function of iteration and found the minimum value and the coordinates where the minimum value occurred. And at the end, we animated the function, animated the motion of the particles in the XY plane. And we found that the system works perfectly. There is no problems with it at all. And the last item, when we animated the swarm motion, I have customized the limits of the measure. No, I have customized the limits of the designer object only, and I did not introduce the measure within the plot contour function. You can see here that this is the mark point, and there is no mesh inside, and the axis values were between -1 to 2 and -1 also to 2 for the y coordinate. Today we shall do two new things. At first we shall carry out animation with the same structure of the program, but we shall leave the default values of the x and y as they are done by Python. And also we shall keep the measure limits the same as they were. Generally, these default values are the values for a sphere, and they are between -1 and 1 at the x-axis and -1 at the y-axis, and the same values are given to the limits of the measure. As you can guess here, if the coordinates begin with -1 point, so the upper right corner will be 1 coordinate point. But for Rosenbrock, this point will be the optimum situation, the optimum place where optimum value occurs. So when we run the program now, we shall see that all the particles are gathering there at the upper right corner of the plot. Let us try it. So I will show you instead of trying, because you remember it may take time. So here is okay, now here is the cost function. Indeed, its final value is 0, and it is about 0, and the coordinates x and y equal to 1. This is 1 practically, and this is 1 practically. And if you look at the position, here is the point x equal to 1 and y equal to 1, which is the red point here. This is the mark point. If I run the program now, okay, I run it. I hope it will not take that much time so that you can see it. So we shall see now, after a while, that all the particles are gathering at that upper right corner, which is not the most appropriate point indeed. The point should be somewhere within the figure area. So as a general approach, we need to customize the axes of the designer. They are not going to be -1 and 1 for the axis x and -1 and 1 for the axis y. I have to change them so that the point 1 and 1 will be somewhere in the middle, or at least it should not be at the corners or the borders of the figure. Well, here is the case. Now you can see, let me now run the program from here, and you shall see that the particles are gathering at this upper right corner, which is not the correct situation indeed. So what we are going to do, we are going to change or to customize the values of the axis. This is one thing. And the second thing is we are going to introduce also the measure within the function plot contour function. We have to introduce there the measure, and the measure also should be with new limits to the values. So the measure, as you look at my pointer here, now is assigned to a function Rosenbrock, not sphere. And now the values are given for the limits -2 and 2 for the axis x, and -1 and 3 to the axis y. The levels here are also changed. And delta, which is the distance between the contours, is kept the same as it is in the original default case. The designer now is also changed between -1 and 1.5, which means that the point 1 now shall be somewhere in the middle, about the middle of the graph, and -1 and 1.5 also. So when I run this program now, of course, I shall get the cost function as usual, it is 0. And of course, it will give me correct answer. Here is the value. The optimal value is 0. And the position is 1 and 1, as you see here. So it's okay. And now, if you look at the figure here, where the animation took place, here is the point minus the point 1, 1. This is the point 1 at the axis x, and it is the point 1 here at the axis y. So it is here. And all the particles are gathering in this point. To show you that again, if I now run the program from here, you shall see that now another picture indeed, and the coincidence or the convergence of the points is in this point away from the corner. Of course, I could also shift it somewhere here or here, or it depends on what you want. I tried also to do the same, but with other values. In the next example, I didn't change anything except changing the measured values and the designer values. And sometimes, if necessary, I will change the levels. Here, the levels are kept the same. I didn't change them. I have changed the designer values from -1 to 2 instead of 1.5, -1 to 2. And the values of the limits of the measure are given -1 to 2, also -1 to 2. The results here does not depend on that because we are changing the things which affect the behavior or the location of the animation process, but concerning the finding the optimum values, it is kept without any change. I didn't change the number of particles or the number of iterations or the function itself. I didn't change anything there. Now, if I run the program, now we see, I think it is here. If I run the program, it is a little bit shifted here. If I run the program again, you can see that the system is working very nice and in an appropriate place within the mesh. If you want again to see the animation from the file which is saved in the computer, I have given it a name called plot3rosen.gif. We can go there, plot3rosen, okay, plot 3 rosen.gif. Yes, it is. Now, if I go to the file and see where it is, where this function here it is, if I open it, I can run it also and see the same picture as I have seen it when running the HTML function. So, as you see, we have done a good job here. We have finished with minimizing the Rosenbrock function in the two-dimensional space, but we want to do the same in a three-dimensional space. So I have to open again my notebook and go to open the file and explain to you the structure of the program. And then I will run the program and show you how the particles also converge to the same point when in the X, Y, Z coordinates. Now I am here. I shall go to the code. This is the last case, I think, which we have seen. Yes, and this is our function here. So we are here. We are going to optimize Rosenbrock in three-dimensional space. Of course, now we need to import some additional libraries and modules in order to be able to animate this function. But concerning the pyswarms, we have imported the pyswarms as before, and the NumPy library also as before. We have imported the Rosenbrock function from the functions module, as we did before, nothing new here. Matplotlib is also imported as PLT because we are going to animate the function. Here, something new. We have to call from multiple toolkits library and plot 3-dimensional module, and from there we import axis 3D so that we can establish a 3D graph, 3-dimensional graph. And from matplot library also, we are going to call the animation module, and from it we import the FuncAnimation class. This FuncAnimation class really, which is going to do the job and which is recommended normally to engineers to work with it. Also, we shall import the HTML from the IPython display. We have also to import, of course, the measure. Why did not the designer? Let me write also the designer. Import measure, comma, designer. And in order to plot the cost, we import plot cost history. I think this is the most important now. So we begin our work. At first, our function is named Rosenbrock. We assigned this name to a variable and we called it objective function. Number of dimensions for this function is 2, x and y, so we write 2 is assigned also to the variable in dim or dimensions. The bounds of the function are the same as we did in the previous lecture. We did not change the bounds because it is specific for this function. They are given as an array for the lower limits, minus 5.15, minus 5.12, I'm sorry, and for the upper values also plus 5.12, plus 5.12. So if we print the bounds, we will find from minus 5.12 to plus 5.12 for both. Here I have printed them. When I run the program, here minus 5.12 plus 5.12, this is for the x coordinates, and the same thing for the y coordinates. Okay, so concerning the bounds, we did nothing. We have just kept them as they were before, and they should not be changed because they are specific to the function. Now, concerning the design of the pyswarms, we keep the option coefficients the same as we did before. Number of particles, I have given them a number of 40. And now, from the pyswarms, for single objective function optimization, because I told you the Python and the pyswarms can carry out optimization for functions for cases with multiple objective functions. This is not our case. We are working only now with one objective function, so we call the single module, and we call from it the global best particle swarm optimization. Note here the big letters G, B, and P, S, O. All these this is a name and given such that and should be kept the same. You cannot change it to small letter, for example. So this is the function which it is going to minimize and find the minimum. We pass to this function as we did yesterday, or the number of particles, which is the same as we have here. It is 40. It is called number of particles. The dimensions is called ndim here, which is, I can write here 2 directly, dimensions equal 2, but for more generality, I write it ndim. And the same thing we can say for the number of particles. I can write here equal to 40 directly. The bounds is equal to the bounds, and options is equal to options. So all the information required for global best PSO are known and defined for the function, and we call this setup as an optimizer. This is the optimizer. Now this optimizer, we call the function optimize from it, and pass there the function, the name of our function, which we are going to optimize. We named it, as you see here, objective function. So I write here objective function. And number of iterations, I have given it 600 iterations. Really, I have done this especially after 1 or 2 trials, because I found it needs a high number of iterations to converge completely, the swarm to converge completely. So this optimizer now is ready to give me my answers, the best value here, the best optimization value, the optimized value, which is 0 in our case, and the best position, which is 1 and 1 as we did before. It is here, of course, you could write here position, POS, any value, right? And here you can write instead of best position, and instead of best value, you can write cost, for example, or best cost. It depends. So, but at the end, this optimizer gives you the result of optimization, the minimum value where optimum occurs, and the coordinates where minimum occurs. Okay, now from the optimizer, I call the cost history, because here the best value, this is an array practically, and there is the values, different values of the cost, or which is defined for each iteration. So it is a history. It is called cost history. So from the optimizer, I call the cost history and assign it to a variable called history. Now I shall have here not an array, I think I shall have here a list with one value of the cost. Here only one value I have. Array with list with one value of the cost value for each iteration. And if I want now to plot the cost history, I have just to pass through it the cost history. This value, the variable, is passed through the plot cost history, and now I shall have the plot. So if I print plt show, which is matplot library, I shall have this function, which is usually done. This function, this is the cost, and this is the iteration. So I have plotted again the cost as a function of iterations, not more. Up to now, this is which has been done here. So plot cost history with cost history passed to it. I get the function of the cost as a function of iterations. To see that, I have asked the program to print the best position. As I told you, this will be a number of values. And this is the 600 values. And this is the best 600 positions. And they are 600 values. But these positions, as you see, are positions of the particle, which means X and Y. They have X and Y coordinates. Every point has X and Y coordinates. Okay, now, as we did for the cost, because from the optimizer we can get the cost history. From the optimizer we can also get the position history. And this is very important because when we are going to draw the particles in a three-dimensional space, we need to know all the values of the coordinates of all the particles. So we need to know the history of the position in addition to the history of the cost. So here we ask the optimizer, this is the optimizer, we ask or we call from it the position history and we assign it to a variable, we call it position history 1. This position history 1, as it is designed by the pyswarms engineers, will be a list. It is not an array. In order to work with it later on, we need to convert this list to an array. This is by Python easy to do. NumPy dot array, and you pass to the array function the name of the list, position history 1. Now I shall get an array which is called, or I gave it a name, position history. So if I print this position history now, I shall get an array, and this array has 600 values. Each position value is an X and Y. This is the array. So if I want to know the dimension of this array, this is an array now, the dimension of this array, it will be 600 iterations with 40 particles, and each particle will have 2 positions. This is the expression of the shape of the array. Before converting the position history from a list to an array, I cannot get this shape. This shape is specific only for arrays and not for lists. For this reason, I have converted the list to an array and gave it a name of a variable called position history. And now this position history, I can print it, print position history, shape, I want now the shape. It will give me 642. 600 iterations. Each iteration will include 40 values because we have 40 particles, and each particle will have 2 positions. If I want to print, really it is too much to print this 600. Every one particle will have 40, sorry, every one iteration will have 40 particles, and each particle will have 2 positions for 600 times. It is really, it will consume a very big table here. So instead of doing that, I shall show you 2 specific values. The first value is I want to print position history. This is the array position history, but I want to extract from it only the 40 positions of the particles, the first 40 positions, and for the first iteration only, the values of the first iteration, the 0 iteration, position history with index 0.1. Also very interesting to know the position history for the last iteration, which is the number 600, to see there what are the final values of the positions of the particles. If we go directly and look at them now, you see the position history itself, as you see, has begun with this value x and y. This is x, this is y, this is x, and this continues 40 times, because this is for the first iteration, one iteration only, for the first iteration. Now, if I look at the final iteration, I gave it a name. I think it is named pH, print pH, and position history for the final or the last iteration. I shall get another values, but these values will represent, of course, the values of the positions at the end. Remember, all the particles are supposed to converge to a value equal x equal 1 and y equal 1, or around that. Look, for this first particle, the final values of the coordinates is 0.9991. The second particle 1.7, 1.2. The third one 1, 1. This number 1 and 1. All of them are very near to 1. All of them are now has already converged to 1, 1, 1, 1. This is an indication to you that in numbers that the process has converged to a position of 1 and 1 at the iteration number 600. So again, I am here. I have asked the program to print for me the positions, the position history of all the swarms at the first iteration only, and to print the position of all the particles only for the last iteration. And we have seen really what is there. This is just a check, quick check while doing the design of the program. Now we are beginning to prepare ourselves in order to write the piece of code which is required for animation. First of all, the function FuncAnimation, which is used FuncAnimation, which is used by which is really called from matplotlib, requires that you have a figure, and you assign this figure and tell the FuncAnimation function that this figure is going to be animated. So we need to create a figure and to create axes of this figure, and we need also to guarantee that the axes are 3-dimensional and not 2-dimensional. So at first we call from PLT, we call the figure function and assign it to a variable called fig. Now the figure is available. Then at this figure, we have to create the axis, XY axis. So from the figure, we call add subplot function. This is a function, and pass there this important keyword projection equal 3D. And we assign it a variable AX. So now we assigned three-dimensional axis, which is required by the FuncAnimation. Additional but interesting things to do is to give the label of the axis, set X label and call it X, for example. AX set Y label and call it Y. And the third dimension here, set Z label and call it objective score. Because really, it is proportional to the objective function. Note here, the letter Z is small letter and not big letter, as XY. Now, concerning the bounds, we also need to set the limits of X and Y. We shall keep the values which are given by the bounds. We will not go and change them. So AX we call set X limit, and we call also from AX set Y limit. From the bounds here, the bounds are known to us, well known. Now, this 0 is the lower limit, this is the X, this is the lower limit, this is the Y, this is the higher limit of X, this is X, and this is the higher limit, and this is Y. So when you look at bounds with index 0 and 0, this means lower limit for X scale. This is the lower, one the higher, this is X, and this is Y. So when we print Kx or Ky, we will get the same values defined by the bounds, which are minus 5.12 and 5.12. So it's okay, we did not do anything new. But now it is known, these limits are known to the function. Now we continue our work. We shall prepare ourselves for this function, FuncAnimation. First of all, we need to define which function we are going to work with. It is Rosenbrock. So func is equal to Rosenbrock, or func, or another way, Rosenbrock is assigned to the function. And this is function now is known to the measure. And we gave it a variable name m. Why we do that? In pyswarms, as you have seen before, we have got two coordinates X and Y for each particle of the 40, for the 40 particles X and Y only. But in three-dimensional space, we need the third dimension to be known to the function to work with. There is a facility in pyswarms. There is a function specifically designed in pyswarms called compute history 3D. This function, only you need to pass to it the position history, which is two-dimensional, which we know before, which you have seen before. So we pass here the optimizer is calling the position history. So here we have the position history passed to the compute history 3D function. Now we shall get here another array, three-dimensional array, with a name, we call it position history 3D. So now we have an array of 3 dimensions, X, Y, and Z. If we want to see what is there, I have given here a test. Show only, here you see only the first iteration for all particles with 3 coordinates in each. Look, here is the number of iterations, here is the number of particles, and here is the positions. So I want to see for the first iteration, number 0, the index 0 is the first iteration. 2 dots or the colon here means all particles, the 40 particles, and here all the coordinates, which is 3. Now it will be 3 positions, X, Y, and Z. From where Z come? It came from here, from the compute history 3D, which has converted the position history to a 3-dimensional or a 3-column array. So if we print this, the name is called position 3D. If you go down to position 3D, here it is. With a little. Yes. Now you see this array with the 3 positions. This is the position 3D. This is the X, this is the Y, and this is the Z. This data is for the first particle, and this data is for the second particle, and so on until the 40 particle. All these are only for 1 iteration. Suppose you want to print for 600 iteration. So you will go this manner 600 times, and every time you will get more and more, because for the first iteration you have got only this 40. For the second iteration you will got this 40 and another 40. For the third iteration 40, 40 and another 40. So this is a very tedious and unnecessary work to do. Now I think it is enough to understand what is going there from this presentation to you. Okay, so now we have prepared the array, 3-dimensional array, which the function is going to work with. The function also asks us to prepare or to give the initial, or some people call it init, the initial or init situation of the X and Y and Z positions, and then to show how these positions are going to change for every iteration. For initialization here, look, it is not difficult, but maybe it seems to some of you difficult because you hear about it the first time. So the position history, we are going to initialize the X coordinate and the Y coordinate and the Z coordinate. So the position here is defined for all iterations, all particles, and this is the 0 position. This is the initial X coordinate for all 40 particles for all iterations. This colon means all iterations. This colon means all particles, and this 0 means the X position. So it is now known. Position Y is also initialized for all the iterations or the particles for the Y position, not X position. The index here is 0. The index of Y is 1. The index of Z will be 2. This is the third index, 0, 1, 2. So I also, Z coordinate is initialized by position history 3D now. It is taken from this array for all particles, for all iterations, all particles, and for the height Z. Now they are all known to us. So we can now if we know all these initial values, so we can draw a scatter plot from AX scatter plot, and we pass to the scatter plot X, Y, and Z. And that's it. The color will be blue. The marker will have a shape of empty O, and the label is called particles. So I will get the particles shown in a scatter plot. And this is essential because we want to see every particle and how it will go to move. Now, how we animate the motion. The function is called animate. Some people call it update. Also, we can say update. It is common, really, to use update instead of animate also. So when we want to animate the position history, we want to see for every index of iterations from I equals 0 to I equals 600. We want to see the positions of the 40 particles for the X coordinates. And for the Y position, we want to see for all iterations, for all from iteration 0 to iteration number 600, for all the particles coordinate number 0. And with the same thing we can say for the Z position now, 3D, for every iteration, for all particles, the position with index number 2, which is the height. Now you need to update, to change from 0 to 1, from 1 to 2, from 2 to 3 up to 600. This is done by using dot offset 3D function. Dot offset 3D function. So the particles which are going to change will update their positions X and Y and Z. This is used to update particle positions and the Z values also. If you want to give a name or a title for this, you can give it a title. But for now, we have defined the initial setup for X, Y, and Z, and we have shown how they are going to change with iterations, and what we need to pass the animate function, and to pass the initialize function, and to pass the other required information to the FuncAnimation class. So FuncAnimation class now, we pass there the figure as a figure. To this figure, we pass the figure which we have established. We pass the animate, this animate function, to the function. The frames number, which is equal to the position history shape of 0, which is the frames number or the iterations number, because shape of 0, you remember, iterations, particles, positions. So the iterations is the 0 index, and there are 600. So frames are assigned the position history shape for the 0 position. Of course, I could take this away and write here equal to 600 for simplicity. But this is really a more general approach and more interesting approach. The interval between the frames is given 150 milliseconds, and I am asking a program when doing iteration and the iteration is finished not to repeat it. I will repeat it if I want. We have created a legend, and the location of the legend at the upper left point of the figure. And then we are going to save the animation in a file called plot47gif. And we write this animation by ImageMagick Writer, which is installed in the computer. And as usual, we use the HTML here in order to watch or to see the animation in the notebook. Well, believe me, I know that some of you has a thought or thought that this is a difficult thing to do or this is not that easy to do. This is just for the first time. When you go deeply and slowly, step by step, you will see that this is not a magic. This is really a normal work. Everybody can do it. And now let us run the program and see what will happen there. So I have to mark the cell where my program is and carry out the running. No, okay, let me see. Is it running? Yes, the program is going on and we shall wait maybe 1 to 2 to 3 minutes for it to give information. The program have just been optimized. The cost is equal to a number multiplied by exponent to the power of minus 21. You can see that this is practically 0. And the positions are 1 and 1. So, okay, as we expected, the values are the same. Where the time goes for the animation. We have also got the first list of positions for the first iteration, as we have done here. And we have got the positions of the first iteration of all the particles, the 40 particles for the last iteration. And now we have changed the two-dimensional array to column array to a 3-column array, so that to take in consideration the height will be a function of the Rosenbrock function. And now we are waiting just to show us how the particles are converging to the optimum minimum of this function. Here, as I told you, we have to wait a little bit. Yes, it is still going on. You need to be patient for this because the result will be interesting and it gives you a warm feeling that what you have done is not vainly done and everything is as designed and as expected to be. So let us wait a little bit. And as I imagine, this will take maybe half a minute or 1 minute more. Yeah. Okay, until it converges, let me give you an idea about what I have done here. If you look, yes, here, this line here, z equal objective function of point P for every point in position history 0, and with the same analogy, objective function of the point P for every point in position history I. This code line of code here, and this line of code here, exactly can do the same as what I have done here. Z equal position history 3D and Z equal position history 3D. I found this is more appropriate really, but you can use this line and this line as I did, or you can stop this line by putting a hash in front of it and stopping a hash in front of this one and work with this one. I'll show you this in the next example. It seems to me that the program has worked, yes, it has worked out its job. And well, we can see our here the point where they have converged. This is a 3x, y, and z, three-dimensional space. This is x to 0. Here x2. So this point here is x equal to 1, this level. And this is y0. And this is y1, practically. So really, the process converged to x equal 1 and y equal 1. But you want to see it. Let me show it to you now. Look. Marvelous, yes? Excellent work. Now, what more? You can also go to the file named plot47gif, and also you can display from there this file, and it will work fine. Let me try to be sure. Plot47gif. Plot, sorry, I have done wrong thing maybe. PLOT, plot 47 dot GIF. Is it? Yes. Now if you go here and we look, here it is. Very nice. So the program works fine, no problem at all. It is giving excellent results. As I told you just now, in this program here, I have kept everything as it was before, except for instead of I, comma, colon, comma, 2, I have introduced Z objective function of P for P in position history I, and the same thing, Z equal or is assigned objective function of point P for P in position history 0. These two lines of code are used instead of the two lines which I have shown you before. If you run the program, you will get the same answer. I can show you also that this will give the same thing without any change. How many number of iterations here? Is it 600 the same or a little bit less than 600? Of course, 350 here. Why I guess that? Because when I looked here, not all the particles converged to the mint point. That's why I thought that the number is a little bit less than before. If I give it 500, it will converge completely. Okay, I think with this, we finish with animation of particles in Python. And now I shall move to show you very interesting work, how to do the same by using LabVIEW. Some of you have sent to me a note asking why I didn't show in the previous lecture the LabVIEW work. I really answered them that this will be done in the coming lecture, which is this lecture. So I want to show you also how we do it. Firstly, I will show you how we can plot the Rosenbrock function by using LabVIEW. Here we have I think this function here, 61 or 60. Okay, if it is not, I will change it. No, it is not here. I am sorry. I'll go back and select, I think it is this one. Yes, it is here. So what do we have here? Here we have many shapes which were created by using LabVIEW. This is the Rosenbrock Valley shape, and it is also drawn in another place. This is the Rosenbrock Valley shape. It is drawn here by using a function here, Rosenbrock, by using a function called plot surface. Plot surface. To work with the plot surface, you need at first to open the front panel of the LabVIEW, as for example here, and you can right-click and select the graph and go to the three-dimensional graph, and from here you select the type of three-dimensional graph you want. I selected surface graph, and now when you put it here and you go to the front panel, you will find it there. Here it is in the front panel. This is the graph, and now I have to connect to its terminals the required things. How we do that? So at first, you need to put in the front panel and the terminal of the block diagram the plot surface with the display connected to it. How it is done in LabVIEW? At first, the first case here, I used a function called evaluate y equal f of x 1, 2. This is the function. How it comes? Where it is? I right-click here and go to the mathematics in LabVIEW and go to scripts and formulas and go to one-dimensional, two-dimensional. Here it is. This is the function which I am going to, no, not this one, another one. Okay. X1 and X2. This is the mathematics script, one-dimensional, two-dimensional. Here it is. This is my function here. This function requires as an input here a start value, which will be an array, and the end value will be an array. You remember as the bounds which we did with Python, there we used -5, -5, 5, 5, for example. Here -2, -1, it depends. You write what you want. But these are array which defines the lower values. This is the lower value of X. This is the lower value of Y. This is the upper value of X. This is the upper value of Y. They are input to this function. What you need to input to this function, also you need to input the function which you are going to draw. Here it is, Rosenbrock, 1 minus x squared plus b, which is 100 multiplied by 1 minus x squared, all of it is squared. This is the function which I am going to plot. This function also requires to give an idea what are these variables, x and y. X and y. These are the variables, and they are given also as an array. Here is the number of points which you are going to use. You can use 25, you can use 40, 100, whatever you want. This is the inputs which you need to input to this function. It will give you as the output an array of x, another array which represents y, and here is the function which is similar to the function as the output of the mesh grid of Python. This is did as a two-dimensional mesh grid output. So this two-dimensional mesh grid, two lines, dimensional mesh grid output is called the Z matrix. And we call and so consider hence the Y matrix. It is here called Y vector. It is an array, one-dimensional. This is two-dimensional. And this is the X vector, which represents also one-dimensional array. The work is done. Now, if you run this program, you will get this output. This is the output you get. Of course, you can turn it the way you like. Okay. Let us go to the front panel again, to the block diagram. We have also a modification of this function, which is called evaluate if of x1, x2 as here, and a. What does this a means? A, coefficients. Here is the input which represents a. These coefficients are the coefficient a, which is multiplied by the first term. Here what was 1, I put it 1. And b, which is 100, I put it 100. And I do not need to include this one and this 100 here within the function. The function now without coefficients. It is just a way to simplify the things and to make them more standard. I have given the low or lower limit -5, -5, the upper 5 and 5. Here I could do that here before, just to show you the number of points. Instead of 25, let us make it 50, for example, or anyway, 50 or 59, no problem. And now if we run, oh, okay, this one will help to be taken. And now if we run the program, we shall get, of course, this shape. This shape also, this is the valley shape, as you see, as U curvature of the Rosenbrock, as we expected. Suppose we change the multiplier instead of 100 by number 5. It will change? Yes, something will change. If 100 here, I changed it by 5, for example, 10. Usually, they use 10. And I run the program. Let me also change it here. Instead of 100, I will put it 10 and to compare between both results. And run the program now. You see? Another perspective. And it is here the same. Let me go back and see. Windows, block diagram. It is 10, 110, there 110 also. 1 minus x1 squared, all of it squared. Yes, plus x2 minus x1 squared, all of it squared. It is okay. There is no problem. The idea is here, the different coordinates. So I should write here minus 2 and here minus 1. Then I can get the same shape. 2 as a higher limit, 3 as a higher limit. And now if I run the program, sure I shall get very similar shapes. Yes, here is the shape down, here is the shape up. Okay, so these are two ways how we can plot by using LabVIEW. But not only this way, I can show you also another way, a third way how to do that, but not with this program, with another program. I shall try to show you that. I will go out from this program. Okay, save. Let it be useful. And I will go to 63, number 2. I think this is my 63, number 3. Remember, when we worked with Python, we first created an array of named X variable, another array which is called Y, and this X and Y were passed to the mesh grid function, and we took as the output new XY values which are two-dimensional. Here in LabVIEW, we have also a similar function, create mesh grid two-dimensional. So you pass a first array. This is the Y array. This is the X array as the input, and you will get at the output here the mesh grid Y array and mesh grid X array. And now these two values are used, X and Y. I use them to build newly the Rosenbrock function. I got 1 minus X, all are squared. Then I took Y minus X squared, all of it are squared, multiplied by 10 or by 100, and then added to the first. So the output here is Rosenbrock to this function, which is called plot parametric VI. And here the X matrix, and here the Y matrix. How these functions comes also the same way as we did before. You go to the front panel, here, go to graph, and from graph to three-dimensional graph, and I went to the, let me remember which one of them, the parametric, this parametric graph. I put it here, it is. And when I go there, here it is. Plot parametric, plot parametric. If you go here and see, you will find that here it is, okay. Let me show it to you. You will see that here, it requires a matrix Y, a two-dimensional array, two-dimensional array X, and two-dimensional array which represents the Z. So now it is clear. If I run them, I will get also something similar to what I have got in the previous two cases. When I run it, here is the U-shape valley of Rosenbrock. This is 5 minus 5 to 5. I gave the range so that they will be very close. Of course, I can take this minus 3 and this 2, for example. I will get another shape somehow different. Let us try. Let me run it again. Here. Okay, so now we have plotted the Rosenbrock and LabVIEW by using three different ways. Don't save. Then what is left? I need to show you how we can optimize by using LabVIEW and how we can animate. Here in LabVIEW, animation will be done only by using a surface and not in three-dimensional case. Really, it could be done, but I didn't do it for you. It takes time, and I kept it for further activities. So, where we are here, let us go. I am sorry. I am talking with you, and I have forgotten what to do. No. We need to go to this file and to optimize in LabVIEW and see this very interesting program. Okay, so here is our program. Here is our function. It is the same function, Rosenbrock function. This is the front panel. Here we shall display the animation. The program itself is here. To work with this program, it is not that difficult. This part of the this is not more than a specifier which gives you information as a code about this piece of code. As you see, here is a path. This means that we get information from a file and feed it to OpenVI reference, and this is the reference. We shall use for this purpose this program which carries out the process of optimization and animation at the same time. This function is called global optimization VI, where it is not difficult. We go to the mathematics, we go to optimization, and we shall see here global optimization. This global optimization function is very appropriate for Rosenbrock because Rosenbrock has only one global, and it is the only minimum value it has. It doesn't has another local values. It has only one this global value. So it is very appropriate to use this function to find a global minimum. Okay, so we shall use it. This function, in order to work, as you see, uses a reference to the place where, to a program practically, where our function is existing. This Rosenbrock function is not existing in the memory of the computer and only called to the function here when we run the program. If you go and double click here, this is a front panel of this sub VI, and we go to the block diagram and see what is there. Here I have drawn or constructed 1, 2, 3, 4. I can draw more, and maybe 5 different programs, which any of them could be called by the main program to be implemented. In this case, here is the Rosenbrock function, and this is the output of the Rosenbrock function, which is connected to a compound arithmetic, and then it is converted to an array to the objective function. Now it is this terminal which is there in that block diagram. Here, as you see, the index array, this is index array. Here is a list. Here, an array here, not a list. I am indexing it, taking the first value as an X and the other value as Y. The upper value is taken as X, the element, and this is as Y. So now this X, here X minus 1, and this X minus 1 is squared. I found X minus 1 squared. Of course, I can do 1 minus X squared. It will give the same result. No difference. 1 minus X squared or X minus 1 squared gives the same result. Okay. We have to add to this Y. This is Y. Minus X. This is X. Squared. And all of them are squared. Now the output is Rosenbrock. And this is Rosenbrock now is connected to the program. When we will run the program, it will run only Rosenbrock. But for Rosenbrock, remember, we need to work with the given bounds minus 5, minus 5, 5, 5. If you want to work with another function, you need to put here another limits which are designed or specific for another function. So these are the limits which I have put here are those required by the Rosenbrock. They are added together here as an array. Here another array. And these two arrays now are concatenated, are bundled, sorry. And this bundle now, it is a type of cluster fed directly to the function. So these are the bounds fed to the function. Here, input, the beginning state is a 0 state, as we do. You remember when we have talked about the initialization of the X and Y and Z, we gave them X equal to 0, Y equal. So this is 0 values and we do not interrupt it. What else you have here is an input where you can define the number of particles. I have put them 50. There could be 30, 20 as you want. And the number of iterations as written here, the number of iterations is given as 50 iterations. At the output, we shall get the minimum value as an array. And we shall get an array of the coordinate because X and Y, this is an array, 2 values here. If you double click here, you shall see this is 2 values. And now The other value at the output here is the value of the function of the minimum, which as we expect equal to 0, as should be. So these are the values is the result of optimization. And if we want now to see the particles and the motion of the particles, we take this output ending state and bundle it by population and take the parameters here and take the X and Y values here as arrays, and they will be displayed here. Now, what this is the X and Y space where the particles are supposed to be shown and to converge to the value of 1 and 1. Here X, here is Y, X of 0 here, so 1 is here. So as should be, the value should be in this line on the X equal to 1. This is Y from 0 to 2, Y equal to 1 here. So our point expected to be here. If we run the program, these are our particles and they are converging at this point. And the values of the coordinates in numbers are given 1 and 1, that is equal to 1. And the value of the function itself is 0. If minimum, as you see, 2 multiplied by the exponent to the order minus 26, it is the same as here. This is at the 280 or 300 iterations. They have already confined, they have already converged before then this number is reached. The number here could be changed by changing this number here from 1000. Let me stop it and write here, for example, 100. And it will be sufficient. If I go back now and run it again, they are gathering closer and closer to the 1 point, and here at 100 it will stop. This timer is put intentionally here so that you can watch how the convergence takes place by time, by iteration, because every iteration means one time, it means 100 milliseconds. I can make it, of course, slower. Let me say 1000, for example, the delay, which means 1 second. And if I run the program, you will see that these points will move, but they will move slower than, you see, slower, but they are gathering and gathering, converging closer and closer to the Y equal to 1 and X equal to 1. Well, I think for those who were eager to see LabVIEW and how it works, I hope that they are satisfied now. And I think that as a beginning, this is a good idea. And for those who are interested to know more and more, of course, they have to make more practices and to read more detailed information about each of the elements which compose our here iterations 46, not 100. Look, it is about 100, it will converge as I expected, but it takes time because the time delay which I put here is 1 second for each iteration. Now it is 61. Around 100, it will converge completely. Yeah. Okay. With this thing, I finish my lecture. I would like to thank you all because maybe I have took a lot of your time. Thank you for listening. Wishing you the best and goodbye.